This is Dr. J.V. Kaspal. In this session, we'll discuss about the stiffness method for sway problems, sway frame problems. So, analyze the portal frame shown using stiffness method, draw BM bending diagram and deflector shape. So, a frame is given here. We need to write first whether it is a sway frame or non-frame. So, given frame is a sway frame. Why there are different levels are different and load is also unsymmetric. So, it is so the given frame is a sway frame. Next, first step is degree of kinematic independence. So if you see here, how many degrees of freedom are there? At B, there are generally 3. At C, and there are 3. But here, the vertical movements are restricted because as it is fixed support here at A and D, there is no vertical movement. So vertical are cancelled. Then 4 will be remaining. What are they? Theta B, theta C, and delta at horizontal movement at B and horizontal movement at C. But horizontal movement at B and C are same. If you see this figure, so horizontal movement is same at B and C, that is delta. So only 3 unknowns are there, no? Theta B, theta C, and delta. So the kinematic independence value is taken as degree of kinematic independence value is 3. Theta B, theta C, and delta. Only one delta we will take because they are same. So generally degree of freedom is 6, but practically vertical movement will be there. So vertical movement will not be there. No vertical movement will be there. So vertical degree of freedom can be cancelled at B and C. As the given frame is a sway frame, there is a horizontal degree of freedom at B and C. But as the displacement at B and C are same delta, we will take only one degree of freedom. So therefore degree of kinematic independence is 3. Theta B, theta C, and delta. Therefore the K matrix is 3 by 3 matrix. Step 2, finding fixed random moments. So same step. So MFAB, MFB as we have calculated in the non-sway frames, same step. MFAB, MFBA, MFBC, MFCB, MFCD, MFDC we can calculate. We will calculate based on the loads. If we extend this, if we put like this and this like in this way, and we can calculate as a continuous beam also. So for here there is a eccentric load, therefore the formulas for eccentric load is this one. Here there is UDL on BC, therefore W square by 12 plus minus plus. So as there is no load on CD, it is 0. Next step 3, assigning the coordinates and calculating the restraining forces. Here we need to assign the coordinates first for the unknowns. So we will take this as theta B, first coordinate, second coordinate, and third coordinate. That means at B we will take first coordinate theta B. At C, theta C is the second coordinate, and the horizontal movement delta is a third coordinate. So now we will calculate the restraining forces P1, P2, P3, which is also called as delta DL1, delta DL2, delta DL3. The formula for P1 is at joint B. What are the fixed end moments? MFBA plus MFBC. So that is MFBA plus MFBC. At C, MFCB plus MFCD. But what about this delta P3, delta L3, third coordinate? It is R1 plus R2. What is R1 plus R2? See, we need to take reactions like this for A, B, and CD. R1, R2. So as it is for delta beam, we should not take the beam. Only columns we need to take. Because we know that delta is only for the columns, not for beams. Yeah. So R1, R2. So how to find the R1? Apply sigma moment about A equal to 0. And show all the fixed end moments here at A and B, MFAB, MFPA. Calculate R1. R1 we will get 25.92. We have assumed left side, so left side means sign convention is negative, so minus 25.92. Therefore R1 plus R2 is this one. So P1, P2, P3 is we will get these values. Okay, P1 plus P2, R1 plus R2, MFBA plus MFBC, MFBC CB plus MFCD, then R1 plus R2. Yeah, next step. So in the next step, we will calculate the stiffness matrix K. K11, K12, K13, K21, K22, K23, K31, K32, K23. So what is K11? Due to the unit rotation at first coordinate, what is the value of K at first coordinate? Next, K12 means due to the unit rotation at first coordinate, what is the value of second coordinate? Next, K13 means due to the unit rotation at first coordinate, what is the value of third coordinate? Next, due to the unit rotation at second coordinate, what is the value of first coordinate? What is the value of K at first coordinate? Due to the unit rotation at second coordinate, what is the value of K at second coordinate? Due to the unit rotation at second coordinate, what is the value of K at third coordinate? Due to the unit rotation at third coordinate, due to the what is the K value at first coordinate? Due to the unit rotation at third coordinate, what is the value of K at second coordinate? Due to the unit rotation at third coordinate, what is the value of K at third coordinate? That is the meaning. So removing all the loads and applying unit rotations to we need to apply unit rotations to find the K values. First of all, let us find K11, K12, K13, the first row. So let us apply unit rotation at the first coordinate, that is at B, that is at theta B. We need to apply the unit rotation. So see here, we have applied the unit rotation. We have applied clock for BA, we have applied clockwise unit rotation, and for BC also we have applied clockwise. Now, so here, what is the formula for BAK? 4EI by, we know that it is a 4EI by L. So 4EI by LBA. Next, here far end it is fixed, so 0. Now for BC, here it will be 4EI by LBC, and here it will be 2EI by LBC, clockwise, clockwise. Next, what about K13? K13. K13 formula is, see here, to the left side we need reaction. The formula is 6EI by LBA square. 6EI by LBA. 6EI by LBA square. This is K13. Now, so here as we have taken clockwise rotation, so clockwise rotation, therefore these reactions we need to take anti-clockwise directions here. This is both are in anti-clockwise direction. So we have taken in this way to the left side. The value is 6EI by L square here and here. See here, if this support is given as hinged support, we need to take it as 6EI by L square. Here it is minus, so we will get plus. But as in this problem it is fixed support, we will have got 0. Yeah, so minus 6EI by LBA square. So K11 is sum of these two. K12 is this one, K13 is this one, minus 6EI by LBA square. So next, how to find the second row? K21, K22, K23, applying unit rotation at C, that means second coordinate. We will get K21, K22, K23. So K21, so where is the figure? Yeah, this is the figure. So here we have applied unit rotation for, first we will see for CD. At C, we have applied unit rotation. For CD, we will get here 4EI by LCD, and here it is 0. Next, for CB, it is 4EI by LCB. Opposite end 2EI by LBC. Now, what about the delta? It will be 6EI by L square. How? See here, as it is clockwise, we need to draw it as anti-clockwise. Both is, so here in this way, the reaction should be shown in anti-clockwise. So here we have written also here. See here, as the rotation is clockwise, the reaction should be anti-clockwise. So the value is minus 6EI by L square. As it is to the left side, we need to take minus 6EI by L square. So in this way we can find, so what is the value of K21? K21, 2EI by LBC. Why K21 we have taken? Because it is when we apply the unit rotation at second coordinate, what is the value of K at first coordinate? So when we apply this at second coordinate, what is the value of at first coordinate? So this value, 2EI by LBC, K11. K22, when we apply unit rotation at second coordinate, what is the value of K at second coordinate? Sum of these two values, 4EI by LCB plus 4EI by LCD. Next, K23, when we apply unit rotation at K, what is the value of K at third coordinate? That is K23 minus 6EA by LCD square, LCD square. Next, let us find K31, K32, K33 by applying unit displacement. See here, we are applying unit displacement at B and C. At B and C, we need to apply unit displacement. There unit rotation, here unit displacement. So as the reactions applied here are clockwise, rotations are taken, rotation at B and C are taken as anti-clockwise. So here, first of all, we have taken the reactions as clockwise here. See, first we need to take the reaction, means this value. So the formula here is 12EI by L cube. So first of all, let us see for at B joint for BC. So the formula for K is, the formula is 6EI by L square. Same here, the formula is 4EI by L, no? Like that here it is 6EI by L square, 6EI by LBA square. Okay. As it is taken as clockwise, these values, as the reactions applied are clockwise, we have taken this as anti-clockwise. So what is this value? Minus 6EI by LBA square, not BC, because this way is only for columns, not beams. Next, for CD, so we have taken anti-clockwise here, here and here. Here it will be 0. For this, here it will be 0. So minus 6EI by LCD square. Next, so this is 2, the formula here is 12EI by L cube. L cube means LBA cube. 12EI by LCD cube. Okay, now k31 value is this one at first coordinate. Due to the unit displacement at third coordinate, what is the value of k at first coordinate? Minus 6ei by lba square. Due to the unit rotation at third coordinate, what is the at delta, what is the value of k at second coordinate? K32 minus 6ei by l square. Due to the unit rotation at third coordinate, what is the value of k at third coordinate? Means 12ei by l cube ba plus 12ei by l cube cd. In this way we can find k31, k32, k33. So in the next step we need to find the unknowns using the relation p plus kd equal to delta d, or delta dl1 plus kd equal to delta dp, delta d. So in this problem delta d is 0 because there are no external moments. So these values we have found already, p1, p2, p3, delta dl1, delta dl2, delta dl3 in the previous step here. So these are the values. In k means already we have found just now, that is a k matrix, and these are the unknowns, and 0 0 0. So by solving it we will get theta b, theta c, delta b and delta c as 14.23 minus 7.15, 45.46. So next step 6, slope deflection equation. Using the slope deflection equation we will find the final end moments. So MAB equal to MFAB plus 2A by L 2 theta A plus theta B minus 3 delta by L. So here MFAB we know 2A by L theta A. So theta A is 0. Why? At A you will have a fixed support. So at A it is theta C is 0. At D theta C is 0. Okay. And for AB and BA we will get delta here. Delta we have to substitute this value. See, for BC and CB, there is no delta value. Delta value substitute 0 because we know that sway is only for columns, not beams. BC is beam here. Okay, only for columns, not for beams. Next, for MCD, in the MCD formula, delta D will become 0. Then you substitute values, you will get this one. And you can draw the bending moment diagram by using these sign conventions. These are the free ending moment bending moment diagram for eccentric load, maximum bending moment. Value. This is for UDL maximum bending moment value, WA square by 8, here WAB by L, and these are the final moment values. Using these sign conventions we can draw the bending moment diagram. So this is way how we solve the sway problems. So for sway frames for using the stiffness methods. Thank you. This is Dr. J. Vikas Paul.